Welcome back to AI.Code.Cast. Today we're going to do a deep dive all about sharpening your coding skills with a classic problem.
Oh, yeah.
The Partition Equal Subset Sum.
I like this one.
Get ready to flex those algorithmic muscles.
This one's a favorite in coding interviews and challenges.
Yeah, why is that?
It's deceptively simple at first glance, but trust me, there's a lot to unpack here.
Okay, lay it on me.
Yeah.
What's the challenge?
So imagine you have an array of integers.
Right.
Like, let's say,
Mm-hmm.
1, 5, 11, 5.
Okay.
In brackets.
Got it.
The question is, can you divide this array into two subsets where the numbers in each group add up to the same total?
Okay, I see. In this case, it seems pretty straightforward.
Right.
You could group the 1, the 5, and the 5, which adds up to 11.
Yep.
And then have the 11 on its own, also summing to 11.
Exactly.
But I'm guessing it gets a lot trickier than that.
Absolutely. What if the array had hundreds or thousands of numbers eyeballing? It wouldn't cut it.
Right.
Plus, this problem has real-world implications.
Oh, really? Like what?
Resource allocation,
Oh.
load balancing in systems,
Oh,
even cryptography relies on similar concepts.
wow.
Yeah.
So where do we even begin to tackle this? My brain's already starting to hurt a little.
Sure. Let's start with a naive approach, just to get a feel for the problem structure.
Okay.
It's what we call the brute force method.
Brute force sounds intense.
It is, in a way. Imagine trying every single combination of numbers in the array,
Okay.
adding them up and seeing if we get half the total sum.
Yeah.
We'd essentially exhaust all possibilities.
Okay. I can see how that would work. Eventually.
Right.
But wouldn't that take forever, especially with a massive array?
Exactly. The number of possible combinations explodes exponentially as the array grows.
Right.
This is where the concept of time complexity comes in.
Uh-huh.
Brute force has a time complexity of O of 2 to the n, where n is the number of elements in the array.
So the bigger the array, the more impractical brute force becomes.
Exactly.
It's like trying every single route on a map to find the shortest path. You might get there, but it's not efficient.
Precisely. And that's why we need smarter algorithms.
Okay.
This is where dynamic programming comes in.
Dynamic programming. It's like the superhero of algorithms,
Uh,
swooping in to save the day.
well, it's definitely more efficient than brute force.
Okay.
Dynamic programming is all about breaking down a problem into smaller, overlapping subproblems
Right.
and storing the results of those subproblems to avoid redundant calculations.
So it's like remembering the best path you've already found instead of recalculating it every time.
Exactly.
I like where this is going. But how does that apply to our partition equal subset sum problem?
Okay. Think of it like building a table.
Okay.
Each entry in our table will represent whether a certain sum is achievable using a subset of the numbers we've seen so far.
Okay, I'm picturing a spreadsheet here.
Mm-hmm.
Rows for numbers.
Yep.
Columns for possible songs.
You're getting it.
Okay.
We start filling this table systematically.
Okay.
Let's say we're looking at the fifth number in our array. To figure out if we can reach a certain sum, including this fifth number, we only need to look back at the results we've calculated for the first four numbers.
Ah, so we're building upon what we already know.
Exactly.
Clever.
Yeah.
But isn't there something about top-down and bottom-up dynamic programming?
Yes.
Which way are we building this table?
Great question.
Mm-hmm.
You're right, there are different approaches.
Okay.
Top-down dynamic programming, also called memoization,
Uh-huh.
starts with the original problem and breaks it down recursively.
Okay.
It's like starting at the peak of a mountain and figuring out the best paths down.
Okay.
If we encounter the same subproblem again, we just use the result we stored earlier.
So it's like having a map with notes saying, already explored this path.
Precisely.
What about bottom-up?
Bottom-up dynamic programming builds up solutions from the smallest subproblems to the largest.
Okay.
It's like laying the foundation of a building brick by brick. For our partitioning problem, we'd start by figuring out which sums are achievable, using only the first number in the array, then the first two numbers, and so on.
Got it. So we gradually build up our table of achievable sums, and eventually we can see if we can reach the target sum, which would be half of the total array sum, right?
Exactly.
Okay.
And by doing it this way, we avoid the exponential explosion of possibilities that we saw with brute force.
Right.
It's all about working smarter, not harder.
This is already making a lot more sense,
Good.
but I've heard there's an even more optimized way to do dynamic programming for this problem.
Yes.
Something about using a 1D array instead of a 2D table. Is that right?
You're thinking about space optimization.
Okay.
While a 2D table helps visualize the concept, it can use a lot of memory, especially for larger arrays.
Yeah, that makes sense.
The 1D array optimization is all about being more memory efficient.
Okay. Color me intrigued. How do you pull that off?
Well, to understand that, we need to dive into the specifics of how we build and update this 1D array. It's a clever bit of logic that lets us achieve the same result with less memory overhead.
All right, you've officially piqued my curiosity. Let's unpack this 1D array optimization and see how it works its magic.
Let's do it. We'll break it down step by step and make sure it's crystal clear for our AI.Code.Cast listeners.
All right, let's get down to business with this 1D array optimization. I'm ready to level up my dynamic programming skills.
It's all about making our solution leaner and meaner without sacrificing efficiency.
So where do we begin with this 1D array magic?
First things first, we need to find the total sum of all the numbers in our array. We'll call this total sum. Now here's a quick check. If total sum happens to be odd, we can stop right there.
Wait, why is that? Is this some kind of shortcut?
It's more of a fundamental rule. You can't divide an odd number cleanly in half, right?
Right.
So if the total sum of our array is odd,
Yeah.
there's simply no way to create two subsets that add up to the same value.
Ah, that makes sense.
It's like trying to split a pizza with an odd number of slices evenly.
Exactly.
Not gonna happen.
Precisely. So assuming our total sum is even, we divide it by 2 to get our target sum.
Okay.
This is the magic number we're aiming for.
Mm-hmm.
Each of our two subsets needs to add up to this target sum for a successful partition.
Got it. Target sum is our finish line. If we can find a subset that reaches that sum, we've cracked the code.
Now here's where the 1D array enters the scene. We create an array of Boolean values, true or false, with a size of target sum plus 1. We'll call this array DP.
Target sum plus 1. Why the extra space?
Remember, in many programming languages, arrays start indexing at 0.
Oh, right.
We want to be able to represent every possible sum from 0 up to our target sum. That extra slot allows us to include 0 itself.
Ah, right. Right. 0 is a valid subset sum, even if it's just the empty set. Okay, so our DP array is set up. What's next?
We initialize the very first element of our DP array, DP 0 to true.
Why do we do that? Is it because a sum of 0 is always achievable? Exactly. We can always create an empty subset that sums to 0. It's our base case, our starting point. Now here's where the real magic of dynamic programming happens. We're going to iterate through each number in our original array.
Okay.
Let's call the current number num.
So we're picking up each number one by one and seeing how it affects our possible sums.
For each num, we need to update our DP array. This is where things get a bit tricky. We're going to iterate through our DP array, but from right to left.
Right to left.
Yeah.
That seems a bit backward. Why not the usual left to right way?
It's a crucial optimization. By going from right to left, we avoid accidentally double counting any subset sums. Imagine we're at index 5 in our DP array, which means we're considering a potential sum of 5.
Okay.
If our current num is 2, we want to check if DP3 was already true, meaning a sum of 3 was achievable before we even considered this new num.
Because if DP3 is true, then adding our current num of 2 would make DP5 true as well.
You've got it. But if we were going from left to right, we might accidentally set DP5 to true based on a newly updated DP3 from the same iteration. That would give us the wrong answer.
Okay, I see the danger there.
Yeah.
Going right to left prevents that kind of mix-up. It's like making sure we're only building on solid ground.
Exactly. So for each num, we go through our DP array from right to left. If we find a dpi that's true, meaning a sum of I is already achievable, we then check if I plus num is within the bounds of our array.
Because if it is within the bounds, we know we can now reach that sum I plus num by combining our current number with an existing subset.
Right. We mark dpi plus num as true. And we keep doing this, moving from target sum down to the value of num itself.
So each number we process helps us expand the possibilities in our DP array.
Yeah.
We're especially building a roadmap of achievable sums, and once we've processed all the numbers.
We check the final destination D of target sum.
Okay.
If it's true, we know we found a path to a subset sum that's exactly half of our total sum, which means we can partition the array. If it's false, then no such partition exists.
This 1D array optimization is impressive. We're building up our solution step by step, reusing information, and doing it all without hogging tons of memory.
It's a great example of how a little cleverness can go a long way in algorithm design. But we're not done yet. Remember, there were a couple of other approaches we mentioned earlier, bit manipulation and hash sets.
Oh, right. We've only explored one path up the mountain. What other routes can we take?
Let's delve into these alternative solutions and see how they compare to our dynamic programming approach. Each one offers a different perspective on the same problem.
Okay, so we've covered dynamic programming with both the 2D table and the super efficient 1D array.
Right.
It's amazing how we can optimize for both time and space.
It's a beautiful thing when efficiency and elegance come together.
Yeah,
But let's not forget about those other paths we mentioned.
right.
Bit manipulation and hash sets that
That's-
each bring something unique to the table.
Bit manipulation always sounds a bit intimidating to me,
Yeah.
like something out of a hacker movie.
Yeah.
How do bits help us solve this partition problem?
It's not as complex as it sounds. Instead of arrays or tables, we use bits to represent which sums are achievable.
Okay.
Think of it this way. Each bit in a binary number corresponds to a possible sum.
Okay, I'm listening. How do we connect bits to sums?
If a particular bit is set to 1, it means we can achieve that corresponding sum using some combination of numbers from our array. If the bit is 0, then that sum is not possible.
So it's like a series of yes-no flags.
Yep.
But encoded in binary, I kind of get it. How do we actually use this bit magic to solve the problem?
We start with a bit mask where only the 0th bit is set to 1. This represents our base case.
Okay,
We can always get a sum of 0 using an empty subset.
right. Our starting point. Then what?
Then, as we process each number in our array,
Ah,
we perform a bitwise left shift operation on our bit mask.
okay.
This shifts all the bits to the left by a number of positions equal to the current number.
So if our current number is 3, we shift all the bits 3 spots to the left.
You got it. This shift has an interesting effect. It essentially adds our current number to all the previously achievable sums that are represented by 1s in our bit mask.
Ah, I see. So if we could previously achieve a sum of 5 and our current number is 3, the left shift allows us to represent a sum of 8. It's like we're dynamically updating our possibilities with each number.
Precisely. Then we combine this shifted bit mask with our original bit mask using a bitwise OR operation.
Okay.
This merges the newly achievable sums with the ones we had before.
So our bit mask keeps growing, encoding more and more possible sums as we go through the array. And at the
You
end,
simply check if the bit corresponding to our target sum is a 1. If it is, we know a subset exists that sums to half the total, and we can partition the array.
that's pretty slick. We're essentially using bits as a compact way to store and track a whole bunch of information about achievable sums. But what about the hash set solution? How does that one work?
The hash set approach is all about efficient membership checking. Remember, hash sets are great at storing unique values and quickly telling us if a specific value is present.
Right. So instead of bits, we're using a hash set to keep track of our possible sums.
Exactly. We initialize our hash set with the value 0 representing our empty subset. Then, as we iterate through our array, we consider each number and add it to all the sums that are already in the hash set.
So if we have a sum of 5 in our set and our current number is 2, we add 7 to the set.
Precisely. And the beauty of a hash set is that it handles duplicates automatically. We don't need to worry about adding the same sum twice.
Got it. We keep building up this set of achievable sums. And once we've considered all the numbers in our array...
We simply check if our target sum is present in the hash set.
Okay.
If it is, we found a partition. If not, then no such partition exists.
So we've got 3 very different approaches to this problem. Dynamic programming, bit manipulation, and hash sets.
Yep.
It's amazing how the same problem can be tackled from such different angles.
And that's the beauty of algorithm design.
Yeah.
There's often no single best solution. Each approach comes with its own trade-offs in terms of time complexity, space complexity, and even the readability of the code itself.
It's like having different tools in your coding toolbox. The trick is knowing which tool is right for the job.
Absolutely. If memory is a major concern, the 1D dynamic programming or bit manipulation might be preferable. If we're dealing with potentially massive numbers, bit manipulation might be risky due to integer overflow issues.
So it's a matter of understanding the constraints of the problem and choosing the most appropriate solution.
And sometimes the most elegant solution isn't the most efficient, and vice versa. It's a balancing act between practicality and cleverness.
This has been a fantastic deep dive. We've explored 3 unique solutions to the partition equal subset sum problem, each with its own strengths and weaknesses.
It's a great example of how a seemingly simple problem can lead to a rich exploration of algorithms and data structures.
Absolutely. And that's a wrap for today's AI.Code.Cast.
Thanks for listening.
We hope you enjoyed this deep dive into partitioning arrays. Let us know in the comments which solution you found most intriguing, and feel free to share your own code implementations or alternative approaches. Until next time, happy coding.